Next up is Roelof with deep learning and deep data science. So can we have a round of applause for Roelof?
Yes, hello everyone. Thank you all for coming. First of all, I want to apologize for the very blatant title, or maybe a bit pretentious. So let's just stick to the deep learning for now, especially since this morning we already had our batch of data science. So yeah, my name is Roelof Pieters. I do a part-time PhD at KTH in machine learning, deep learning, natural language processing. And also I work part-time as a consultant for my own consulting company. But first, before we kick off, something really important. Are people here cat persons? Can we have some hands? Cat persons? Yeah? Dog persons? Yeah, it's pretty much 50-50. So I wanted to basically have this presentation on something more creative than the always cat and dog examples, but it's actually quite hard to find good data sets, in this case for images on different examples. So I promised a friend to come with maybe squirrels and cats, but squirrels were hard to come by. So I stuck with cats and dogs. So in the next few minutes, we'll be making our own cat versus dog classifier. And we'll be doing this using deep learning, which is a special branch of machine learning. It's kind of hot at the moment, and we'll try to explain a little bit about it first of all. And then in the second half, so 10 minutes of maybe an explanation and generally what it all means, so what is behind the buzz. And then 10 minutes of actual maybe doing some coding and showing, well, how can we use this actually. So the libraries which we'll be using, which most of you might know, scikit-learn was already mentioned and I misspelled it. So it's one of the most used machine learning libraries, I can say. We'll be using Caffe, which is one of the various deep learning libraries, mostly used for computer vision, this one. It has wrappers for Python, C++, and all kinds of other languages, but mostly it's used for Python. And we'll also be using a little bit of theano, which was actually the announced description of my talk. But because of lack of time, I opted for some higher level libraries. And I also will be using IPython notebook for the coding part. And if that not works, then I prepared some screenshots of IPython notebook in the presentation, then we can pretend that it's all very interactive and nice. So scikit-learn, it's the website. So it's really easy to get started for different kinds of classification or machine learning tasks. There's plenty of examples which you can run and just download. It's really good documented. So it's like, I would say, the single best source to get started if you want to do some machine learning. Then Caffe again, which is one of the main developed libraries. And what is nice about Caffe is that it comes with a lot of models, pre-trained machine learning models, deep learning models, which we'll be using for this talk. Just a pre-trained model, because training a deep learning model will take us 2-3 weeks. So instead, we just load a pre-trained one, and we'll be using that. theano. And then also we'll be using actually PyLearn2, which is a wrapper on top of theano to make it a bit easier. But if you're a researcher and you're really interested in the more detailed aspects of what is going on in the different deep learning and steps, etc., in your algorithms, then theano is the place to go. It's a nice library. It has symbolic operations to actually compile functions, so it is highly efficient. So you can create your functions before actually running them. I already put the input in the expected output in there. And it's also, all of this is optimized for GPUs as well. And of course, the IPython notebooks, which also now supports actually other languages. So, bear with me. Sorry, it was late at night when I found this. Get it? Bear. So coding will be ahead, but first, some words about data science. And if there's any questions or things, or please interrupt me, and maybe we can have some small questions if they're not too long, but more about what is going on here. So short questions, maybe we can already ask them, and then leave the more detailed questions for the 5 to 10 minutes after. Because I will try actually to rush a bit through this, because I expect most people to know at least some of this. The slides will be online as well, and the IPython notebook I will be also putting up if you want to play with it yourself. So first of all, data science. Generally, it's well described by Hilaire Mason and Chris Wiggins that it's a bunch of different things together, but mostly that it combines a certain kinds of ethic, so a hacker's ethic, which mostly means that people want to be creative and play around and try new things. It combines statistics, which means that as a data scientist, you not only have to be kind of averagely good in machine learning, but also in statistics and machine learning. And then there's some other ideas about this with the Venn diagram, quite famous Venn diagram by Drew Conaway, again, the hacking skills, the math and statistics, and then also expertise, or I would call more programming. So you actually have to combine both statistical understanding with a bit of programming. And that's kind of what is exciting about it. So it's both very theoretical, if you want, and you can kind of decide yourself how theoretical things are, but it's also very practical, yeah, in the sense that you actually code stuff and you see things happen. To basically explain the difference between machine learning and deep learning, it's kind of interesting. One of the reasons why deep learning has become very, very successful and very much used, it's the fact that with machine learning, we researchers, computer vision, natural language processing, audio processing, for many years, 30 years at least, have been mostly focused on the features. So which features are important? Next to the pre-processing of the data. So we want to have very good features, manual feature engineering, a lot of time goes ahead, and every year we might have a few % increase in our models, in our accuracy, but nothing really drastic. So there's a lot of expertise needed, like for natural language processing, which is my field. Linguists, battle together about what are the best ways to represent grammar and rules, and then come to kind of different ways to maybe find the grammar of a string, of a text, etc. But important to know is that when you have the data, and especially when you have very complex data with a lot of different kinds of features, and you want to find a good model which represents the kind of meaning behind this data, the structure behind the data, the more features you have, the better. So you can actually see that both of these, might be similar data, but if you have at least another feature to compare them, the dogs from the cats, it's easier to divide them from each other. So with this, maybe it works, but it tends to overfit because it's too much, it basically overfits on your data, so it will not do much. You have more features, it tends to do less of that. So we can have a better classification or a separation boundary, like so. And the more features in that sense, the better. So we would say, okay, let's collect a lot of data, harvest a lot of data, or big data or whatever, but mostly we'll have this kind of data. But then there's also problems there. Well, if you have more data to do these kind of things, then and you want higher dimensions, then actually the data has to grow exponentially with the number of dimensions. So that means you have a lot of data, but ordinary machine learning approaches don't really scale to this kind of size. So this kind of models, which are quite simple classifiers, don't really work. So instead, some smart people came up, mostly, already in the 80s and the 70s, but in 2006-ish, it became more widely known, with deep learning, which can be summarized that it's most of all a host of different machine learning techniques or algorithms, most of all, and it enables automatic learning of features. So instead of being spending a lot of time manually engineering our features and thinking really hard about what is the best way to represent our data, we don't care about that at all. We let the computer decide through some brute force, through neural networks, as we'll see. We let the computer come up with the best kind of features. And we'll do it in a specific way that the features are hierarchical, that the most abstract features will be on the lowest level and the more complex features will be at higher levels. And it's mostly based on actual neural networks. So deep learning model looks more like this. So we have a lot of data, much more data, more classes, etc. But also we have the calendar days. It also means that actually it takes much longer to train the model. So yes, there's no single size that fits them all. So it does mean that your models tend to take longer to be trained, but you have the possibility to model more data and more complex data, more dimensions, let's say, in your data to find a kind of hidden non-linearity or etc. And again, similar summary of that is basically that one of the critiques thrown also at machine learning versus deep learning is that at least on the feature level, which I just want to focus, is that manual features tend to really overfit easily. They're hand-designed, they're brittle, and they're very specific to your specific data you have created this feature for. So they don't scale to other kinds of data sets. So if you have a more generalistic model which can do more things with the same model, then it's easier to use them and also easier to adapt to different other domains. So in deep learning nowadays, you have models, for instance, which can both understand text, but also images and also audio in the same kind of model. And it can find, how do these different modalities still connect to each other and what are kind of, how are they similar in their structure. And mostly when we talk about deep learning, we also talk about unsupervised machine learning. So there's no labels. So that's most of it, what I wanted to tell about deep learning. Last of all, these are the three conspirators, if they call themselves, or the deep learning mafia. So there's Benjo, there's Hinton and Lacan, and these guys have been working with deep learning or different kinds of neural network algorithms already since the 80s or earlier. And actually nobody really took them serious because it didn't really work. Neural networks were slow. They never could beat the support vector machines. They could only model up to 2 to 3 levels and never much further. But in 2006, both Hinton and Benjo, with their own different way of doing that, came up with a way to model more dimensions than 3 in an efficient way. So it was a kind of nice mathematical trick which allowed you to go past these restrictions. And that kind of set loose the deep learning beast, if you will. So what happened since then is that mostly actually not so much universities, but actually companies and research centers have been started, and a lot of people have started to use these kind of deep learning models, throwing away their 30, 40, 50 years of work of manual features, which is maybe a bit tough to do, maybe also why it's less the case at academics, university levels, but more in companies, especially companies which are more recently started. But here we have audio recognition, and the red ones are the deep learning models, or orange, and the blue ones, it's the traditional models. And these are the different years that this contest in audio recognition was held. Every year there was a little bit of increase, or not so much, even a little bit decrease, etc. in the error rate. And then deep learning came along, and bam, it was an immediately extreme, It was almost like a horizontal line if you would take the average, and then deep learning comes along and there's a big pitfall and it's still continuing. Same for image recognition. ImageNet 2012 was the first big hit by exactly the model which we're actually be using now, because we downloaded the model and we'll be loading it. So that model won the ImageNet competition on object recognition, recognizing objects from images. And since then, basically, it's only deep learning what people have been using, and error rates are drastically going down still. Natural language processing, my field, lagging a bit behind. But of course, it's not all what can be said about it. But for now, let's summarize that people are working hard on it. There are some interesting things happening, but it's not as drastic, at least, not on the same level as it has been for computer vision and audio. So deep learning how? Again, almost at the code, bear with me. We have some, let's say we have a data set. Let's say we have some faces. And a lot of this is not really important to know in details. It's just more that when we get to the code, that you kind of get a feeling of like, what are we doing where, and how does it make sense? I mean, there are some links at the end if you want to read up on it. But it wouldn't really make much sense to just run through the code and say, look, this is what we get as a result. But then you know exactly a bit more what we're actually doing. So we have a data set, we have faces, and then we have our neural network, which is a deep neural network because it has multiple layers. So the first layer is the input layer. So that's where, let's say you have there the pixels one by one. going into, and then you have some hidden layers in between, and you randomly initialize them with a certain weight, and then these nodes, neurons, as they are inspired by kind of the brain, start to randomly guess at what might make sense in a bit random fashion, but then at some point they kind of figure out like what makes sense if you combine them together, and it operates more and more like the brain, where in your visual neural cortex in your brain, the closest neurons you have in your brain are actually what you connect to your vision is the edge detector. So what they see, it's really not so much interesting in itself. It's just a lot of edges, a lot of like lines. And that's what we can see here. So the first layer, it's kind of the edge detector, the lines. Then you have combining those lines in a different layer, the next layer together. You get a bit more detailed. And then the third layer is combining those together, and you have the faces. And this is inspired by the brain, very much different from the brain. But this is actual visualizations from what is inside these kind of neurons. So that's pretty amazing that you can actually get these things. And it also helps us understand more of like how these kind of models can work. So if we take all of this together, we can see that there's different layers. And these layers, they have an input which gets from below to the end, and you have some output, and it's being checked, well, is this correct or not? And then it gets back, well, it was correct or not, and it does something to optimize the neurons in the inner layer. And at some point, it starts to make sense, and you get good results. So that's it. Are we all still here, or? Good. So the coding time. We get to the code. So our ingredients for the code is the Kaggle cat versus dog dataset. So it's 25,000 cat and dog pictures. That's what we have as the input. And from those 25,000, we have the labels. And we do, of course, a split on them to separate maybe part of them for the separate testing set. So this is where you can download them if you want to try it yourself. And then we preload or load a pre-trained neural network. So when we go back to the neural network, basically what we'll be doing. So when you have all these neurons, they all have a certain weight, which basically says, if you combine neurons together, can we fire or not? And this is trained, and it kind of starts making sense at some point. So these weights we can download, and we can plug into our existing model. And that's what we will be doing. So I can save us sitting here for 3 weeks, just waiting for it to happen. So that's that, and it's a specific form of neural net, which is mostly used for image recognition, convolutional neural net. And then, if we have time, but probably not, we'll do something special to actually show how we train a deep neural net. We train a very restricted variant, a multi-layer perceptron, which is a different variant from convolution, a bit more simpler, and also more hierarchical inspired. And that one we will then use, making use of the features which we'll get out of the pre-trained network. And then the hope is that when we feed it with cats or images of dogs, that we get really accurate results, and it should at least be able to beat our support vector machine. So what we'll be doing is we have this neural network architecture, which we have loaded in the Caffe library. And we'll basically be extracting the features from not the end result, because these ones are trained, the end 1,000 neurons, they're trained on, it's a softmax layer in the end, and they're trained on 1,000 classes from the ImageNet dataset. So the ImageNet dataset is a big collection of pictures, of all kinds of pictures and stuff. And basically, we just train that. It's trained, and we're not interested in 1,000 classes. We only want 2. We only want cats, and we only want dogs. But we are interested in some previous layers, which have some conception, quite high-level conception about these images. And we basically use those as features. So that will be our data set for the next layer. So if we do that, we get our features, and we can basically take those from an image. We convert it to a feature, and from those features, we can load it into our neural network. So no freelance, but free models. So Caffe models we can download. So that's how they look like. That's how Caffe basically treats it. We can classify it on the architectural level. So we're not really much interested in the whole, algorithmic part at all. we're very much interested in the architecture. So what kind of layers do we have, and what are we doing with it, which is really nice. So you don't even have to know like the mathematics or whatever if you don't want to. So for the code part, we have some libraries we're importing, and this is standard Caffe stuff. So we basically import Caffe, some pickles objects, and some other stuff, some visualization, matplotlib. And here we load the pre-trained, no, that was me. We load the pre-trained model. So we have two models we downloaded, or one model we downloaded. The first is the architecture file, and the other one is the trained weights. So we load that, and we're loading that into basically the Caffe classifier. It's a very simple, very easy. It takes care of everything for you. So that's the only thing you have to do, and voila, you have your network, which you can play with. And we basically just say that it's the image dimension of 256 by 256. And some more details I will not bother you with. So then the next step, we feed it into the image, which we have, into the pre-trained neural network. So that's what we're doing here. And basically what we do here is the Caffe input, and then we transform the data because we pre-process it to grayscale and things like this. And then the net forward is the most important part in below. All the rest is just details. And that's how we propagate it through the entire network. So we don't have to do much more than that. The network takes care of it itself. And we get some features there from the FC6, which is the fully connected layer we're interested in. Once we have done that, we get more feature info, and we basically feed all the images we have through it one by one. So that's basically how it looks in the image IPython notebook. So we just load them in. That's the function which I made ping to NumPy. So it basically takes an image and it creates some features out of it with the neural network. That's what we're doing. And then we save them dump them as a pickle file. And then I'll skip this part. But basically what we'll be doing is a similar thing with actually creating our own neural network here. And I'm happy to explain more at the bar, but I think I'm getting out of time here. But basically what we're doing is once we take those images one by one, we also save those features in a separate trainer dataset. So this is just the features. We have the features, and then we're interested in making a classifier on top of that. And that's basically what we're doing with PyLearn, which is built on top of theano. And then already after 5 minutes of starting with our deep learning model, which we expect maybe to take 3 weeks, but we don't let it run for 3 weeks. We just let it run for an hour. But already after 5 minutes, we have basically really, really good accuracy. The misclassified is what we're interested in. So we already have here accuracy of almost 94%. And this is how it looks like from the iterations up to an hour. So 100 iterations took an hour. 0 is when we start training. And more zoomed in is when we start from iteration number 2, which actually starts making sense. And the blue line is the training data, the green line is the test data, and they're very nicely, both of them, decreasing, which means that it's not overfit yet. Normally we would have a third line for a separate validation data set. But it means we can probably keep doing this for another 2 weeks. And that's when you get this kind of amazing results of like 99% accuracy or whatever. So I have a Python notebook on the side, but I decided not to show it. But one last thing we can do, because that's basically it. And then I think everybody wants to go for, so here's the Python notebook I will put up on my GitHub. But let's just try it on my own picture. There's a small, I already created let's just go down here. So this is all the code. We can have visualizations. We can see that if we take this one, what we get out. And there is some documentation there as well. And I'll try to document it a bit more if people are interested, but we want to go all the way down. So here we have an image of a cat. And basically what we've got in here, when, let's say, just to show you if it works or not, Well, first we show it on the cat. Does it load it? Of course. That's why it's nice to have it in the slides. Okay, anyway, we had this really beautiful picture of the cat. And when we checked it, then we see that it's actually recognizes it as a cat. And the accuracy we also have, we know it at 97%, which we saw on the previous slides. But then the nice thing, because it's a binary classifier of cats and dogs, we can basically also take all kinds of arbitrary pictures. And this is a very arbitrary one. And because it's on the beamer, it doesn't want to use my webcam. But this was the picture I created from my own face. So that's me when I was sitting in front of here. And then we're going to see, there it is finally. Am I a cat or a dog person? I'm a dog. So I'm very much over time, so.
Now about 4 minutes for questions.
How much certainty was that result?
Sorry, what?
Level certainty.
Well, we don't know. That's more intuitive. But I mean, the interesting thing, if you know what it is, then you can. I mean, the result we got now from just training an hour, it's 97% accuracy on actual cats and dogs. But the interesting thing is because we convert my face to actual really rich features, and then we compare it to, this is just a classification of like, okay, am I a cat or a dog if I would have the classifier on top. But we could just as well just take the raw features, which is really rich with a lot of, dimensions, etc. And we could actually ask from, okay, all the test images, which of the images do I look the most like? So I could actually see I'm not only a dog, but which of the dogs is the most, similar as me. Yeah. Or
how do you go about from the layers to the image representation you were presenting of the features?
yeah, yeah. So how do you get from the images to the input image to the features, right?
No, the other way around. From the layers, you were presenting the features you extracted in a visual way.
Yeah. Well. So you have the layers, and what you can do from the layers is you have the network, and the layers and the nodes in the network, they all have their own weights and biases and all kinds of, like a neural net makes sense. So when you then feed one image into the network, then it will start recognizing the edges, and it will start combining the edges in the next layer, and that you can see. So that's what you represent. So it will be different for every image, but that's the kind of thing you can represent. There. So the final layer should be very much similar to a cat, for instance, or at least how a computer understands a cat.
Excuse me. Over here. Hey.
Yeah.
So I have a question. I mean, this is amazing, and I think, as you showed, all the big companies are doing this in secret, I presume. But I assume you are more sort of familiar with the work that's happening all around the world with this. And so what do you think will be sort of one of the big impacts we can see in the next coming 5 years from this?
I mean, yeah, so there were actually two questions. So one question about what the companies are doing. They're actually really, I mean, the strange thing which has happened is that companies started a lot of research institutes like Google, Baidu, Flickr, whoever, but they're actually really open. I mean, they're even competing with each other, who is the lowest accuracy, and every month it's someone new. And they're publishing papers like rapidly, more efficient than any academic I've seen. They have also more money, of course. So first of all, they really are participating in the academic debate, of course, for their own reasons. So that's one. So a lot of their work is semi-open. They wouldn't publish maybe their code, but at least they publish the results and kind of how they got to there. And then you cannot really compete with that because they will have massive, supercomputers. But at least you can kind of understand what's going on. And then about what is happening in the next 5 years. Well, I hope language processing. I think natural language processing, so language understanding will be like the new big thing. And I'm not alone in that. KTH is also, trying to formulate some research projects on be working with that. But it's right now it's like still the hardest thing to work with as well, because language, unlike images, which are really close to, you know, when we see the world and we have pixels, you know, it's kind of, a pixel is very similar to how it actually operates in our brain. A pixel is a pixel, but language is a construct, and it's culturally different, and it's different in time, and it's already by itself an abstraction of something else we try to represent. So that makes it already hard to you know, represent, because it's so rich and it's also ever changing. Images don't change so much. Language changes all the time. There's like thousands of new words born every single day with the use of Twitter, for instance. Yeah. So I think language, and I hope language.
Hey, so sort of on the same subject, you mentioned natural language processing in your talk.
Yeah.
What are some, so I know there's word2vec, that's like sort of really well used in deep learning. Are there other tools or projects?
Yeah, I mean, without getting too much into technical details, there are some specific neural networks which are really good in understanding sequential data, so kind of sequence data, time series data, which is recurrent neural networks, or recursive. There's two variants. They're both called RNN. So exactly within there, and then there's all kinds of variants like long-term, short-term memory, and etc. There exactly, it's very good for audio, but also especially for language. And there's a lot of work happening there, because word2vec is really nice, but it's not really actually quite deep. It's a very sparse and not so deep network, but it's really interesting. Yeah, and I think Hendrik will give a talk on that as well. Yeah.
Thank you. That is that for this talk, and we thank Roelof. And
yes, and if people want to find me or at KTH, here's my email address as well, or at the company, and I will be at the bar as well.